That is a beautiful 2 Hz signal that we created in the last episode using assembly language. Now, if you watched the last episode, I must admit, the mathematics, specifically the algebra, was probably a little bit hair-raising for those of you who are not mathematically inclined. Nonetheless, we managed to create some incredible code, and it was painstakingly put together with some very precise timing, and then programmed onto this PIC microcontroller, which you can see right here on our breadboard. And if you haven't watched the previous episode, I highly recommend you do that because we spent a lot of time going through that code. But when we left the final episode, we recognized that the code was inefficient. There were more efficient ways to do this, particularly through the use of timers. Just about every microcontroller has some selection of digital peripherals. The timers are the ones that we're going to be talking about today. But before we jump right into it, there is one thing that I wanted to mention, and I apologize tremendously because there was a mistake in the last 2 episodes that I completely overlooked. And it had to do with this specific part of the code. See, 2 episodes, we talked specifically about organizing the code, and we used this directive called org, or ORG, that helps us organize assembly code. Its purpose is to ensure that the next line of code starts at that particular address. And that's all good and fine, but we also talked about labels and the idea that you can use labels to reference locations in the code. And we created a label called initialize. And a little bit further up, there is a line of code that says go to initialize. So basically we're saying go to address 0005, if you remember that episode. But my mistake was that I reversed the order of these 2 lines. And every single time we assembled the program, it actually told me that I had it wrong and I didn't even notice. Look, our custom-made assembler lists all the labels that it's using and identifies the address to which that label is pointing to. And clearly, the initialized label is pointing to address number 1, not 5 like it's supposed to. And that has to do with the sequential way that this code is interpreted. And for this code to be interpreted properly, that org directive needs to happen before the label. That way the assembler knows that that label is associated with that particular address. Now, this little peculiarity probably only affects me because we custom created that assembler. Your assembler may not do this, so don't be too concerned. But I recognize this issue and I had to fix it. Now, when we assemble it, the initialized label is correctly identified at address 005. I know, I'm sorry. We're kind of doing this on the fly. We're on episode 35 of our long-term journey of creating a digital illumination system. And of course, right now, we're in the middle of a small subset of episodes where we're programming this microcontroller. And we started off this little subset of episodes talking about how this entire circuit was designed. And if you're interested in reviewing that, make sure you go back about 2 episodes to see how all that was done. But if you're already caught up, let's dive right into today's topic of timers. We're going to start off talking about the first timer over here, and it's part of this list called digital peripherals. And like I said before, most microcontrollers have these things called peripherals, and they are incredible. I mean, before in our previous episode, we created that timing loop to do the 2 Hz output line by line, and the processor was busy doing everything. But you can delegate some of these tasks to these peripherals, and if you do that, they go off and perform those tasks. And all you really need to do in the main code is just check in on them from time to time, and that way you can focus on other things that you might want to do with your code. Peripherals are awesome. Now, they're not perfect and they do have some limitations, but as we start diving in, you're going to acknowledge some of those imperfections and see some of those limitations. And that's okay. Once we've accepted that those things exist, we're able to work within those boundaries and leverage these peripherals to the best of their abilities. And that's one of the reasons that most microcontrollers have multiple timers. That's because each timer has different features and slightly different limitations, so they work best when applied to the right use case. Fundamentally, timers operate in the same way. Essentially, all they do is they count. You can tell them how fast to count, and they let you know when they're done counting. And if we take a look at one of the control registers for timer 0, we can see that it gives us a list of clock sources. In other words, how fast should this timer count? And the default item is the lowest one in the list. Basically, it's just saying that we could feed an external signal onto one of the pins of this microcontroller, and that signal would determine how fast this counter counts. And we just happen to have an external 20 kilohertz signal that we used in one of our previous episodes. And if we go to the pin allocation table, in the timers column, we can see that T0CKI is an RA2. We can plug in our external clock source onto pin A2, and that will feed our timer 0 clock input. So we're just going to plug in our external clock into pin 2 right over here. This white wire coming off the breadboard is leading to our scope so we can monitor the signal. We also have another white wire here connected to our scope to monitor the output signal. Taking a look at our scope, the blue line is the input signal or the external clock, and we can see it reads 20 kHz. Back now to the datasheet, we'll take a look at another register also belonging to timer 0, which has a few other settings, but the important one is bit 7. So in order to turn on timer 0, we simply have to enable bit 7. So let's go into our code and add a line where we do just that using the BSF instruction, which targets the 7th bit in the T0con0 register. With that instruction, the timer is now enabled. Now we have to interpret the output. We can get rid of all these calculations and byte movements we did in the previous episode and replace it with these two instructions. If we take a quick peek at the T0con0 register, bit 5 says out, which is the output of the timer. In other words, every time this timer completes counting, it will toggle that out bit. And bit 5 just happens to neatly align with where we've plugged in this LED. It's connected to bit 5 of port C. So all we need to do is copy that timer control register and place it on latch C, and we should see the output on our LED. And that's exactly what this code does. MOVF captures T0con0 to the working register. That's what this 0 indicates. And then it moves the working register to lat C. So let's assemble and program. We got nothing. To figure out why, let's examine one of these instructions very carefully. Let's look at the first instruction we inserted into our code, BSF T0con0, 7. As you know, we can find that instruction in the instruction set summary in the datasheet right over here. And it shows us the binary representation of the BSF instruction. Here they are written out. There's the BSF T0con0, 7 instruction, and this is what the BSF command looks like. You can see the 0101 BBB FFF. We know from previous episodes that BBB refers to a binary representation of the direction value. And in our code, our direction value is 7. And translating 7 to binary results in 111. And you can see how I've lined up the 1s to the appropriate Bs. And all of the Fs in the instruction refer to the target file register. And in this case, that target is T0con0. And looking in our datasheet, it tells us that the address of T0con0 is 059E. So let's write that out here. And converting 059E to binary gives us 101, 1001, 1110. So let's write that down here. The 5 becomes 101, the 9 becomes 1001, and the E becomes 1110. Now let's combine this target file register and the direction value into the BSF instruction. The 01 translates straight down to 01. The next 01 also translates straight down to 01. The next 3 bits become 111, and then the following 7 bits become the F. So it's only going to take these 7 bits and move them down. These 5 bits are ignored. And so what the microcontroller really sees is this instruction. And if we dive into our memory map and look up address 01E, we can see that it's gray. That memory bank address is unimplemented, so we're writing values into, well, nowhere. So of course this code is not going to work. But the clue to our salvation lies in this memory bank map. You may have noticed that it's divided up into banks, and many of these other banks have useful registers associated to them. Scrolling down a little bit, we'll find that T0con0 is located in bank 11. So we need to create another instruction which instructs the microprocessor to switch banks to bank 11 before issuing that BSF T0con0 instruction. And the instruction we're looking for is this one, MOVLB, move literal to BSR. BSR stands for Bank Select Register, so the MOVLB instruction allows us to insert a value into that register, and for our purposes that value needs to be bank 11, or in hex, 0B. So just in front of that BSF instruction, we'll insert a MOVLB instruction. And we mustn't forget to reassign the bank back to 0 before we hit this MOVWF to latC instruction, because as we know, latC lives in bank 0. And then finally, recognizing that we're going in a loop over here, we have to insert another MOVLB instruction right over here to make sure that this T0con0 reference goes to the right bank. Now let's try assembling and programming. Still nothing. Now, resolving this particular problem took me a long time, but eventually I figured it out. The issue has to do with the way we are receiving the external clock on our port A2 input pin. The I/O port chapter in the datasheet talks about this obscure thing called ANSEL registers, or analog select. Diving a bit deeper, we can determine that the ANSEL register determines whether or not that pin is analog or digital. And if you look at the reset value or default value, they are set to 1. And 1 says that it's an analog input. And up until now, we've completely ignored this register, yet we've been able to successfully output digital signals onto the LED. We saw it at the previous episode, we haven't quite gotten it working yet on this episode, but we know we're able to output signals. The problem has to do with the digital or analog circuitry on these chips. If you're pushing out a digital signal on an analog pin, it'll still work. But if you're expecting to read a digital signal on an analog pin, it won't. We need to configure these pins as digital inputs, and the ANSEL register allows us to do that. Now, trying not to forget what we just learned, we got to find out which bank that ANSEL register is in. And it is all the way at the end of the bank list in bank 62. You'll find it right here at address 1F38. So in our code, I'm going to insert another MOVLB instruction to bank 62 or 3E, and then insert a clearF ANSEL A to configure port A as digital. And while we're at it, we might as well configure port C as digital as well. Now let's assemble and program. And it's still not working. Okay, so I see I forgot a step. In our code, we're calling the clear watchdog timer instruction over here, but we're not calling it in our main loop. So yeah, we forgot to feed the dog. Remember in the last episode when we talked about the clear watchdog timer? Well, yeah, we need to make sure that we do it properly here. Now the good news is we don't have to call it as often because in the previous episode we were running on a much shorter or slower clock. This time we're running on a 1 megahertz clock, which means that we only need to feed the dog once every 200 instructions or so. So let's adjust the code to make sure that the dog is adequately fed. And then we can remove this clear watchdog timer because we'll certainly reach this point in the code in less than 250 instructions. And let's assemble and program yet again. Okay, I've officially lost my mind. It should have been working at that stage, so I've been trying to figure out what the problem was. Yeah, I figured it out. There's a resistor back here that's really tough to see, but it was put in place to ground the pin RA0 when we weren't using it. But we're kind of using it now. And of course, I forgot to remove it. Oversights. Now we have a beautiful blinking LED. And confirming channel 1 on the scope, we can see the output at just over 39 Hz. We can find out why this timer is running at 39 Hz by looking at the T0 con 0 register. The default value of bit 4 is 0, which means timer 0 is an 8-bit timer. And as we know, the highest number an 8-bit register can hold is 255. So this timer is counting 255 times before it toggles its output signal. And with a little bit of math, we can use the input frequency of 20 kHz to calculate an input period of 50 microseconds. And if we multiply that period by the total number of counts, which in this case is 256, we get a total delay of 12,800 microseconds. And since that delay will occur on both the high and the low of the signal, we need to multiply it by 2 to get a full period. And of course, inverting the period gives us an output frequency of 39.06 Hz. Exactly what we see on the scope. Now 39 Hz is a bit fast. You probably don't even see the flashing of the LED on the camera. Let's bring this down to a more human 2 Hz. To calculate the number of cycles we'll need, we'll start with our 20 kHz input frequency, which we know is a 50 microsecond input period. A target frequency of 2 Hz requires a target delay of 250 milliseconds. If we divide that target delay by the time it takes our counter to make 1 count, we result with 5,000 cycles. Now we just talked about how the largest value this 8-bit timer can hold is 255, so we can't fit 5,000 into this one 8-bit timer. There is an option to change this to a 16-bit timer, but let's not do that. Let's look at an alternative way. We're going to use postscalers. The datasheet describes this thing called a postscaler, which basically divide the output of our timer by a certain value. And on the datasheet, we can see the largest value is 16. So let's try dividing our output using the 1 to 16 postscaler. The math starts off the same with the input period and the target frequency of 250. To calculate the output, we simply divide the result by 16, which gives us 312.5. which is still too big to fit into a single 8-bit register. Luckily, this timer also has prescalers, which we can use in conjunction with the postscalers to slow it down even more. And the configuration for those prescalers are in T0con1. Scrolling down, you can see the wider range of prescaler options that we have over here. Now you gotta be careful when using pre or postscalers for your timer, because the more you scale your timer, the less accurate the resolution becomes. For example, if we choose a 1:32 prescaler, we can work out the math this way. Here's the input frequency at 20 kilohertz, and it's pre-scaled by 32, so our input period is actually 1.6 milliseconds. Calculating our target cycles using our new 1.6 millisecond value, we get 156.25. Now the nearest integer to that is 156, which gives us an error of 0.4 milliseconds. That's what I mean by resolution. The more we scale our timer, the less precise it can be. But we might still be able to find nice, neat integer values for our scaled timer to land upon. And in order to figure that out, we just have to do the math. The idea is to start small and work your way up. So you could do it manually, or you can use a spreadsheet, like I've done here. I define a target delay of 250 milliseconds or 250,000 microseconds. We've already calculated our timer period at 50 microseconds. This is based on the 20 kilohertz input timer. And then I choose a prescaler. I'm going to start off with 1. And then I create a matrix of postscaler values, and in this case we go from 1 to 16, and the actual timer count along the y-axis. And in this case we go from 1 all the way to 256. And the values inside this matrix represent the error that we would result in if we took that prescaler, the count, and the postscaler, which are all included in this calculation. And our intent is to get this value as close to 0 as possible. So I applied a color shade based on that value to get us close to 0. And we can see based on these values, the closest we can get is 45,000, which is still too far off. So we can adjust the prescaler value in this spreadsheet and all the values in the matrix will change. Let's try 2. If we scroll down, you'll notice that the green actually starts a little bit earlier. And then interestingly, it starts going into the red again as it becomes negative. And scrolling down a bit, we can see that we actually do get a 0. And this occurs at a count of 250, a postscaler of 10, and a prescaler of 2. So if we use this combination of prescaler, postscaler, and count, we will get a precise 250 millisecond delay based on this timer. But in many cases, there are additional matches that may meet your needs as well. If I change the prescaler to 4 and scroll down, we can actually see that we get another hit at 125 count, and a postscaler of 10. But we also get a hit at the 250 count and a postscaler of 5. So any of these options will give us a precise 250 millisecond delay. Let's go with the most recent one, which gave us a 0 at a count of 250. And based on the datasheet, there is another register called TMR0H, which will serve as a period value for the 8-bit register. So this is where we enter the 250 minus 1, because our spreadsheet went all the way up to 256, and the maximum value we can put into a register is 255. And so 250 minus 1 is 249, which results in F9 in hexadecimal. So in our code, we'll move the literal value F9 into the W register, and then move it into the timer 0H register, thus setting the period for our timer. Back in our spreadsheet, the prescaler that we used is 4. And in our datasheet, the prescaler of 4 results in a CKPS value of 2. Which gets inserted into the lower 4 bits of this register. And since the rest of the register will remain at default, we can simply set this register to 2 in our code. And finally, our postscaler, which happens to be 5. And in our datasheet, the postscaler of 5 results in an out PS value of 4, which goes into the latter 4 bits of the T0con0 register. And currently in our code, the only thing we're doing with that register is we're enabling the 7th bit to turn the timer on. So instead of doing that, we'll move the literal 8-4 into the T0con0 register, which will simultaneously assign the 1 to 5 postscaler and enable the timer. Now we'll assemble and program, and look at that. The LED is blinking at 2 Hz, as confirmed on our scope. Now let's do what we did in previous episodes and switch from an external clock to an internal clock. If we exclude the bottom two, we have the option of using the internal oscillator divided by 4, which will be pretty good, but as we discussed in previous episodes, our timer will now be dependent on our system clock, and ideally we want to choose a timer that is independent. That way, if we decide to change the value or change the speed of the system clock, our timer doesn't get affected. Which would exclude the next one as well, the high frequency internal oscillator. But we do have the option of using the low frequency internal oscillator because currently our system clock is based on the high frequency oscillator. But as we also discovered in previous episodes, the low frequency oscillator is inaccurate, which leaves the medium frequency internal oscillator at 500 kilohertz. So the medium frequency internal oscillator is just a fancy derivative of the internal high frequency oscillator, but the important thing is that it's independent of the actual system clock, which means it'll stay at the 500 kilohertz, which is indicated in the datasheet. The documentation also describes the synchronous versus asynchronous mode. And basically it says that if you want to use a timer frequency that is greater than 1/4 of the system clock, you must use asynchronous mode. Now, asynchronous is fine for certain things, but generally you want to try to stick with synchronous mode because using the asynchronous mode means that you might run into some timing issues. It does have some benefits, but we really won't go there right now. We want to stay with synchronous. But if we're going to use a 500 kilohertz timer, that means that our system clock must be at least 4 times that, which is 2 megahertz. Our system clock right now is only 1 megahertz. So in order for us to use the 500 kilohertz timer, we need to increase the system frequency or the system clock of our microcontroller. And we can do that with the oscillator module, which allows us to adjust the frequency from 1 to 32. To give us plenty of room, I'm going to choose 4. And so in our code, I'm going to add a few useful comments, which helps us understand how different timing elements are configured. And we have to remember to check the bank of that oscillator module. It's in bank 17. So we have to include the appropriate MOVLB instruction in our code before configuring the oscillator frequency to 4 megahertz. And then we can make our adjustment to our timer frequency. Now that we know our input frequency is 500 kilohertz, our input period is 2 microseconds. We still have our target delay of 250 milliseconds, so we can adjust our spreadsheet to reflect our new value. And as you might imagine, with the faster clock speed, we're seeing a whole lot of red. We don't start seeing green until much later in the prescaler range. If we set it to 64 and scan through the spreadsheet, we'll find that there actually is no 0. But we do get close right over here with 16. And that happens at a count of 217, postscaler of 9, and a prescaler of 64. Now I looked, but I couldn't find a smaller error, so it looks like we're going to have to go with this one. Now remember, the value we need to put in is 217 minus 1, which is 216, which works out to hex D8. And in our code, we're currently setting it to F9, so let's change that to D8. We also need to change the prescaler to 64, which uses a value of 6 in the CKPS bits over here. And since we changed our clock source over here to the medium frequency, the upper nibble of this register needs to be A, or 1010. So in our code, instead of setting T0con1 to the value of 2, we're going to set it to the value of A6, which equates to a medium frequency internal 500 kilohertz source with a 1 to 64 prescaler. And finally, the postscaler of 9 gives us a value of 8 for the out PS bits. And since we also want to make sure that our timer is enabled, we're going to have an 8 over here as well, since this will be 1000. So in our code, we'll change the 84 to 88. And then on our breadboard, we can remove the external clock and replace it with this pesky 10 kilo ohm resistor to ground. Now we can assemble and program, and look at that. Our LED is blinking again at 2 Hz without an external clock. Okay, so there's something about our code that I'm a little dissatisfied with. It's all this bit over here. See, those few lines of code are in a loop that's constantly being repeated. And with our current system clock of 4 megahertz, that means the instruction clock is 1 megahertz. And working that through, I think it's something like 150,000 times a second that loop repeats. And all that loop is doing is toggling an LED every 2 seconds. I think we can find a more efficient way to do things. Like, rather than updating the output 150,000 times a second, why don't we update the output only when the input changes? In other words, wait for the timer to lapse, and when the timer lapses, you update the output LED. And the T0Con0 register has an output bit that toggles with every completion of the timer. So rather than just simply copying that bit to the output 150,000 times a second like we're doing now, we could simply monitor the bit and change the output whenever it changes. Now, this bit, or the out bit of the T0Con register, is a good choice to do that, but there's even a better choice. There is a register called PIR0, or Peripheral Interrupt Request Register. It's in the interrupt section of the datasheet. Okay, so in an earlier episode, I touched on the fact that we will be covering interrupts in a future video. Today is not that video. However, this register right here will indicate the completion of the timer even with interrupts disabled, which means we can leverage this ability without getting our hands dirty with interrupts yet. So rather than doing this in the main code, we can simply test bit 5 of register PIR0 to see if the timer has rolled over. Don't forget to make sure we're in the right bank. PIR0 is in bank 14 or 0E. So each time we test this, if the timer has not yet rolled over, we'll simply continue our loop as usual. But when it does roll over, I want to call an appropriate handler. If you're familiar with other programming languages, you might be familiar with the concept of a subroutine, a little piece of code that exists somewhere else that you can call from another location of the code. That's precisely what this call instruction is. We're basically asking it to go to this location, which we have not yet defined, and when this subroutine is finished, to come back and continue the next instruction. And then we create the destination of that label anywhere in our code. Generally, I like to put my event handlers near the beginning of my code before the initialization procedure. So I'm going to include an org directive to say that my timer 0 event handler will start at address 005. But our initialization process starts at 005. Well, I can just relocate it. I'm going to give us plenty of space and assign the initialization process to address 100. Now I'll include our handler label, leave a bit of space, and put a return instruction. That return instruction tells the microcontroller to go back to where the call was originally called from. And it remembers where the call came from through this thing called a stack. Now, we don't really need to get into details about how a stack works. For our purposes, the only thing we need to be aware of is that it's a special place in memory that remembers where calls were made from. It works on its own. You don't need to worry about it. We don't need to worry about it. The only thing we do need to pay attention to is how big the stack is. Now, this particular microcontroller has a stack that's 16 levels deep. That means we can make a call from a call from a call from a call 16 times before we exhaust the capabilities of this particular microcontroller. It's unlikely that will use that many calls. So I don't think we need to worry about the stack depth at this stage of our growth in our journey. So with the assumption that the stack will simply work, we can go ahead and add code into our handler. And the first line of code that I'm going to add is this BCF peer05. When our timer overflows, bit 5 will automatically set. This is what our test in the main loop will test for. But that bit only goes back to 0 when we tell it to, and you can read it right here. It says it must be cleared by software. And so that's what this instruction will do. It clears the timer 0 rollover flag. Now we can write the code to affect the output on latch C. And since latch C is in bank 0, we're going to want to make sure that we switch to bank 0. Now I'm going to use a value to create what's known as a mask. And the particular value of 20 means that all of the bits in the register, except for bit 5, is going to be 0. The only bit that will be set is the one in position 5. If we look at the binary representation of the hexadecimal value 20, we can see that bit 5 is the only one that is set. And then we're going to use this wonderful instruction called XORWF. This instruction will take the value in the W register and apply an XOR bitwise operation to the target register. And in this case, we've defined that target register as latch C with the direction value of 1, indicating that we want the output to directly affect the latch C register. The bitwise XOR is basically a selective complement function. So if you remember from a few episodes ago, we discovered the comp F, which complements a register. In other words, inverts the whole register. Now in our situation, we don't want to do that. All we want to do is invert one bit in that register, specifically bit number 5, to ensure that only bit 5 is set high. Then when we use that mask in our XOR operation, whatever is in lat.c bit 5 will be inverted, but all the other bits will remain as they are. It's a wonderful instruction. And as an extra bit of good measure, I want to make sure that we return to bank 14 before leaving the subroutine. Now we can assemble and program, and there is no change to our blinking LED, which means our simplified code works. Earlier when we looked at the list of peripherals, we recognized that there's more than one timer. And we also identified that the timers are a little bit different. Timer 1 is one of those different timers. It's only got 4 prescalers, 0 postscalers. It cannot be configured to roll over at a specific count, but it's got a few special modes that we're really not going to discuss today. One of the other differences with Timer 1 is that upon a system reset, the value of its count is undetermined. So it's a good idea to clear it, set it to 0 on every reset. So let's write some code to do just that. Note that Timer 1 is in bank 4. Looking at the clock sources for Timer 1, we have 2 new options, dedicated 1 MHz signal and a dedicated 32 kHz signal. Let's use the SF 1 MHz signal. Based on that, Timer 1's period is going to be 1 microsecond. And as we just touched on, there is no way to define a period for Timer 1, which means the rollover happens every time Timer 1 exhausts its entire 16-bit count, which works out to 65,536 cycles each time. And working out the output frequency based on an input of 1 MHz, we get 7.63 Hz. So now we'll configure our 1 MHz source for Timer 1 and enable it by setting the 0 bit of the T1 con register, which we can see right over here. Next, we have to test if Timer 1 has rolled over, and the bit we're testing is number 5 in PIR1. Just like Timer 0, Timer 1 has its own overflow flag in the register PIR1, and we'll define a new handler for the Timer 1 overflow. And the first thing we'll do in that handler is clear the associated rollover flag. And also like Timer 1, we're going to create a mask, but this time we're going to invert bit 4 using the hexadecimal value 10. And then apply that mask with our famous XORWF instruction, revert the bank back to 14, and return out of the subroutine. Finally, I'm going to add a few more comments to clarify the parameters for this timer. And then to make sure we can see the output, we have to add an LED to RC4. Assemble and program, and we see our 2 independent timers. If I connect the second channel of our scope to Timer 1, we can clearly see both signals. The first one at just under 2 Hz and the second one at 7.6 Hz. Pretty much equal to what was predicted. Now our code right now is pretty efficient, but sometimes we might be able to get what we're trying to achieve without code at all. There might be a hardware solution. Looking at the pin allocation tables, we can see that in the timers column, there appears to be a timer 0 out function, but it doesn't have an assigned pin. But looking at another part of the datasheet, specifically the Peripheral Pin Select module, it appears there is a way to place the timer 0 output on a pin. And all we need to do to make that happen is insert this particular code into an appropriate register to assign a pin to it. And the register that we want to reassign the timer 0 hardware output to is RC5. The pin that the LED is currently connected to. And the specific register to put that code in is located in bank 62. There it is right there, RC5 PPS. So we can insert some code here to allow us to do just that. Now that we've assigned a hardware output for Timer 0, we no longer need the bit testing and event handling code, which means we can get rid of these 2 lines and this handler and all this. Let's assemble and program. And look at that, both LEDs are still blinking, one via hardware and one via software. Microcontroller peripherals are truly amazing. They allow the delegation of tasks which would be time consuming for the main process to always be managing. It's a wonderful delegation ability that I think I'd like to use as much as I possibly can. Now today, all we've done is we've made a couple of timers turn on and blink. On our next episode, we're going to put these timers to work.